to my YouTube channel, and in this video I'm going to talk about the Otto cycle over here. So now in the Otto cycle is also known as the petrol cycle that we use in gens, in car engines and different type of engines. We have petrol gas and other and many engine oils operate on Otto cycles, and is also known as a constant volume cycle, which is an isochloric cycle. So because it is supplied and rejected as constant volume, that is, when it is supplied it is at constant volume, and when it is rejected it is also at constant volume. So now let us analyze this PV and TS diagram. Now this is how the PV and TS diagram over here. That is the that graph of pressure to volume and the graph of temperature to entropy S. So now from the graph of pressure to volume here, we will note that from 1 to 4 we are having constant volume. I mean, from 4 to 1 we are having constant volume, and that is like the end of the session. But from 1 to 2 here we are having a decrease in volume. That is, the volume is decreasing isentropically. That is, isentropic means that it is reversible, and yeah, it is reversible and it is adiabatic. So this is it is reducing volume. That is, there is a compression. If it is reducing volume, therefore there is a compression in the gas that is being added, and the little space here that is between 2 and the graph there, that is what is known as our clearance volume. In case you have you will see where they talk about clearance volume and all that stuff. So that is it for clearance volume. So now the gas now is compressed from 1 to 2. You can see a picture analogy of it here. This is something like this, whereby this is compressed from this point here to this point here. That is, there is a compression over there if you take a look at it. So now let us come back to what we are talking about here. Now after it is being compressed, when there is a constant volume, there is a constant volume between 2 and 3. So what is happening between 2 and 3? There is a supply of heat. That is, at that point 2 and 3, that is the point whereby the spark plug is creating heat. That is the point whereby there is an heat. That is, you see that at the point 2 and 3 also here, that is temperature. There is temperature and entropy increase in this state. So um we have that for that. And now continuing with our diagram, we have from 2 to 3 there is an isochloric heat addition. That means at constant volume it is being added. Then from 3 to 4 we also have another isentropic, but this now is an expansion, because it starts from the lower volume V3 here to the higher volume V4. That is, V3 is from here, from this point 3 here, to V4, which is from here to here. That is the higher volume to lower volume, and that is the isentropic heat expansion isentropic expansion of gas. So then we also have from 4 to 1, which is isochloric heat rejection. That is the point whereby gas comes out of the exhaust pipe, the black smoke that comes out of the exhaust pipe. So this is an entire this thing here. Line 1 to line 2 is isentropic compression of gas. Line 3 to line 4 is isentropic expansion of gas. Line 4 to line 1 is isochloric heat addition, and that is it. So that is the 4 processes, and these 4 processes has to repeat itself over and over again in an ideal case, and that is why we are dealing now with an standard Otto cycle. That is, this is the ideal one that is going to be looked at for real cases that are going to occur. That is why we are using stuff like isentropic, which is reversible, and naturally gases are not reversible, but we are using reversible cases here, which is an ideal case here. So now, talking about our Otto cycle, we also need to know about the processes. In these processes now, there are like different formulas in which you can use. Now for from 1 to 2 we have isentropic isentropic um isentropic compression. So first of all, we need to know what our compression ratio is all about. Now, our compression ratio here is denoted by this sign here, gamma V. And gamma V here is equal to V1 over V2. So gamma V is equal to V1 over V2, and that is isentropic compression. That is the maximum compression here, the maximum volume here, minus divided by the minimum volume, which is here. The minimum volume here, and this is the maximum volume at this point. And you can see here that V4 over V3 too will still be the same thing as V1 over V2 as our compression ratio. So another thing that we need to take note of is our thermal efficiency. So now thermal efficiency will need to be calculated, which is we need to know the formula for thermal efficiency. And the thermal efficiency in an Otto cycle, or let me say in any cycle at all, is given as the thermal efficiency in any cycle at all is given as our this n here is equals to the work done, work net over our q in, work net over our q in, and that is, and our work net is also known as our change in our the heat added, not the heat added minus the heat rejected. So our heat added is our q1 q in, and our heat rejected is our q out. That is going to give us our net work done. So we can just say that this here is equal to our q in minus our q out divided by our q in. So now that is the formula for that, and our q in minus q out divided by our q in, which, so we can just break this down to become equal to q in over q in over our q in, yeah, q in over our q in here. Then we have minus q out over our q in. So now our q in cancels our q in here, and this will become 1. So therefore we would eventually have this as we will eventually have this as 1 minus q out over q in. So let me just write it there, as this is equal to 1 minus q out 1 minus q out over q in. So 1 minus q out over q in is our formula for, that is our formula for our formula for thermal efficiency. And then what is our q out and q in? Our q out and q in has its own formula. Now our q out is here is our heat added, our q out is our heat rejected, and our q in is our heat added. So now in the diagram over here, our q in is added at this point of 2 to 3, where we have our isochoric heat addition. That is, the heat addition is where we have our q in, that is heat, that is where our heat comes in. So at this point here is where we have our q in, and then at this point here, that is where we will have our q out. That is where we will have our q out. So That is it. So now, if we know that that is the point where we have our Q out, therefore we can, as we can say that our Q in, our Q out is going to give us this. We are going to be having Q Q in would be equals to M times CV, M times CV times the change in temperature, which is the formula for heat. We have times our change in temperature, which is the formula over there. So now what is our change in temperature here? So our change in temperature from 2 to 3, that will be equals to T3 minus T2, right? Because we have it as T3 minus T2. So therefore our change in temperature will be T3 minus T2. Therefore Q in would be equal to, we have M, then we have C times, then we'll open a bracket, here. We have T3 minus T2. Yeah, we have our T3 minus our T2, then we close our bracket. So now that there would be the formula, that this here would be our formula for our Q in, and we can also say the same way that our Q out would be equal to something similar, but now our Q out would be equal to, from 4 and 1, that is Q4 minus Q1. So I mean T4 minus T1. So therefore we would have this as our Q out is equals to, we have M, we have CV, which is our constant volume times change in T, which is, if we open our bracket here, we would have T4 minus T1, and this is our formula for Q out. So now that we have known our formula for Q in and Q out, we just impute them into our equation, which is 1, this equation here, which is 1 minus Q out over Q in, and this is going to give us, this here is going to give, this is going to give us equals to 1 minus our Q out here, which is equals to our Q out, which is equals to MCV into brackets. This is Q out now, which is our change in temperature here is T4 and T1. We have T4 minus T4 minus T1 close the brackets. So that is our formula for Q out. Then we have it divided by Q in. Our Q in is let's change CV into brackets T3 minus T2. T3 minus T2. So that will be our formula for this. So now we see that we have MCV over on top and we have MCV in the bottom. So therefore we can just cancel it out. We can just cancel it out here. As MCV here cancels MCV here, and therefore we would have it as 1 minus T4 minus T1 is equals to 1 minus T4 minus T1 over T4 minus T3 as our formula for efficiency of an auto cycle. So now that is for that. Now we can solve a question over here. We can move on to solve a question over here. Let's take a look at this question here, which is a petrol engine has a bore of 58 millimeter and a stroke of